change immediately. It will take some time to change. Like when this voltage is changing 0 to 1, this voltage will changing to 0 to 1. It will take some time to change. But in reality, we think that it will change suddenly, instantaneously, but it will not change suddenly. It will take some time to change. This is called as what? Transition. Rise transition or fall transition. So now, when this is happening, when the rise transition is happening, when the signal crosses this unit,
अच्छा सिंक्रोनियस मोटर सेल्फ स्टार्टेड नहीं होती है ना, इंडक्शन मोटर सेल्फ स्टार्टेड होती है। वो थ्री फेज अपन देते हैं इलेक्ट्रिक। सिंक्रोनियस मोटर में अपन रोटर को अलग से सप्लाई करते हैं। अच्छा, जब जाके वो स्टार्ट होता है, एक्सटर्नल सप्लाई नहीं। क्या मस्त समझाया ना यार। पाँच कितना 5-6 मिनट का वीडियो है, इतना मस्त समझा दिया जो तू है ना 2 घंटे लगा लिए।
Good morning, everyone. Let us start with this session.
This conference will now be recorded.
Good morning, everyone. Let us start with the session. So today we will be starting off with the AMBA Chai protocol training. So as part of this, we'll be focusing on the latest version of the Chai protocol, that is version E. There are versions from A to E. So we'll be focusing on the latest version of the Chai protocol. First, let's discuss about the schedule for the training. The training will be for 6 weeks. It'll be only weekends only training. We'll have training on Saturday and Sunday, around 3.5 hours on Saturday and Sunday. Okay, and it is available in both online and offline. If anyone interested in attending classroom, they can come down to institute and attend offline also. And we will be providing assignments for every week. Whatever topics we cover, for those topics, we'll be providing you the assignments, so that it will give you a chance to look through the spec and the presentation and question the things and understand the things better. And we'll also share the session notes, and we'll also give you access to the presentation. Now, the agenda will be, it will be an in-depth training, because we are spending almost 6 weeks, close to 35 to 40 hours of training. Each and every topic in the Chai will be covered. So initially, we'll be starting off with understanding the Chai overview. Then we'll understand what exactly is the cache coherency. Then we'll understand the cache line state diagram. I mean, how the cache line states change based on various Chai transactions. Then we'll also talk about the coherency protocol. Then we'll talk about Chai architecture and the topology and the different components that make up the Chai topology. Then we'll talk about component naming. So you'll come across things like request node, home node, slave node. There are different naming conventions are there. What exactly is these things? We'll talk about all those aspects. Then we'll talk about transaction classification. I mean, there are different types of transactions are there. A read transaction, write transaction, dataless transaction, right? So like that, there are multiple types of Snoop transactions. So we'll be discussing about all those types of transactions. We'll also talk about channel overview. Basically, AMBA Chai protocol consists of around 4 channels. So for doing different aspects like request, response, for each thing, there is a dedicated channel. So we'll be discussing about those channel concepts and what constitutes those channels. Then we'll talk about the channel fields, the transaction structure. How does one transaction look like in AMBA Chai? Then we'll be talking about address signals, control and data signals, network. And then you see, going forward, we'll see that AMBA Chai protocol has been implemented in 3 layers: network layer, protocol layer, and the link layer. So we'll be talking about network layer, the protocol layer, link layer, and we'll be then talking about advanced aspects like exclusive access, cache stashing, and the DVM operations, distributed virtual memory operations. We'll be talking about how the error handling works in Chai protocol. And also we'll be discussing about the quality of service. So this is what is the agenda. Even though it list looks smaller, but each topic in itself is a major topic. I mean, each in itself requires 2 to 3 hours to discuss in depth. So that is where the training would require around 6 hours, 6 weeks to go in depth of the Chai protocol. So first, let's start with the Chai protocol overview, how it has evolved, and what is that? What are the features that constitutes the Chai protocol? Let's discuss that. Chai stands for Coherent Hub Interface. What is coherence? Coherent we'll discuss. Basically, it's a concept where you see, you can understand the whole system, SOC, as a masters, slaves. Slaves are nothing but the different types of memories, right? Memory mappings. When we say coherency, every master in the system should have the same view of the some location. Let's say it's like if I take this diagram, let's say there is a location 100 in this slave, AXS slave. So when we say that it's a fully coherent system, this master also should have the same data for 100. Let's say if it is accessing, it should get, let's say, 25 data. If this master is also accessing, it should get 25. If this master also accessing, it should get 25. This would be called as coherent. I mean, you may say, what is there in that? I mean, every component will get the same data, right? When cache comes into picture, that actually the reads and writes don't happen directly to the main memory always. The access happens to the caches. Locally, caches will be there. To that, access will happen. The cache coherency, the coherency is a concept where there will be some kind of interconnect in case of ACE protocol, which will make sure that all the caches gets up to date. As and when some other master accesses that cache, my different cache also gets updated. That is what we call as a coherent system. So we'll talk more about what is coherent system and what exactly is the cache coherency in the following slides. During this discussion, if you have any doubts, please feel free to ask your doubts. Next. See, Chai is an evolution of the ACE protocol. You see, ACE is nothing but AXI plus cache coherency plus DVM operations plus barrier transactions. We call like that. I can say Chai as ACE. I mean, a completely the overall changed model of ACE protocol. I mean, the concepts remain same. The fundamental concepts remain same. Okay. Plus, it supports memory ordering transactions and the features to support support for ARM v8.1, v8.2, and the latest and the other latest ARM architecture features. Basically, what is the changed model of ACE means? To support larger scale, to support scalability and performance. I mean, to be able to add more number of masters to get more bandwidth out of the system. So that is where we go for Chai protocol. In essentially, both ACE and Chai does the similar work: cache coherency, DVM operations, barrier transaction. When you come to Chai protocol, it is the topology itself has been changed. See, ACE is always interconnect based model. This is how ACE based system look like. Multiple masters connected to the interconnect, and on the other side you have AXI port through which you connect the AXI system, AXI interconnect. When we go to Chai protocol, we'll see that this is not the kind of topology Chai suggests. There is something called as crossbar interconnect. That is one thing. There are different topologies. So the user can choose the topology based on the requirements. Let's say if I need performance as a requirement, I can go for one type of topology. So that is where Chai becomes very flexible protocol, where user can choose the type of topology they need based on the specific requirements. So we'll talk about all those things in the later sessions. So I hope you have understood that Chai it's similar to ACE with the changed model, how the things have been implemented, how the access happens, the basic unit of communication, those things have been changed. But the fundamental concepts like cache coherency, DVM operations, barrier transactions, memory ordering transactions, except for this, they remain same from the ACE protocol. So that means if you are familiar with ACE protocol or any other cache coherency protocol, for you learning Chai protocol will be relatively easier. Now, let's go a little deep into this. Chai protocol, there are 5 issues. Issues means 5 versions are there. It's not the issue I'm talking about. How many versions have been released? They are A to E. Chai version A, Chai version E, like that. Okay. Chai A protocol is basically the first version of the Chai protocol, Basically, that is where they have defined the new channels, the Chai terminology, the component naming, everything has been implemented in Chai A protocol. This is the first version of the Chai protocol that has been released. So that is where they define new channels, terminology, everything. They also provide the examples of how the request should be done, how the Snoop filter should be implemented, how the cache happen. All those things are defined in Chai A protocol. Also, it defines the rules for transaction ordering, exclusive access, and distributed virtual memory operations. Talking about Chai B version, it adds on top of A, it adds features for supporting ARM v8.1, ARM v8.2 extensions, system extensions. So I'm not right now talking about the C, D, E, because unless we understand the fundamentals, you probably won't be able to understand what exactly we mean by distributed virtual memory, what are these ARM v8.2 system extensions and all those things. First, let's go through the fundamentals, then you will be able to understand these things better. So around that time, I'll introduce you to all the versions of the Chai protocol. Next. First, let's talk about ACE protocol versus Chai protocol. How do they differ? Let's focus on. First, ACE stands for AXI coherency extensions. Whereas Chai protocol, here Chai is there, which will come later. It provides hub level. Next, ACE has 5 line states. In ACE, if you know ACE protocol, you would know that it has got the cache line. Every cache line is assumed to be in one of the 5 states. Either a cache line can be in unique dirty state, a cache line can be in shared dirty state, or it can be in unique clean state, shared clean state, or invalid state. Whereas Chai protocol, 5 cache line states are there. That is, it can be unique dirty, shared dirty, a unique dirty partial, a unique clean, shared clean, unique clean empty, and invalid. So you see there are cache line states, 7 cache line states are possible in Chai protocol. Then ACE protocol extends the AXI write and read channels. See, as I told you in the previous slide, ACE is nothing but AXI plus the things added to support cache coherency, DVM, and barrier transactions. So it extends AXI read and write channels by introducing separate Snoop address, Snoop data, and Snoop response channels. ACE is a point-to-point topology. ACE supports up to 32 masters in a coherent domain. You can have up to 32 masters. For example, in this case, you have got 3 masters. In case of ACE, you can have there is a provision of up to adding 32 masters. Whereas in Chai protocol, it classifies different components in a system by node type. Each component is treated as a node, and each node has one ID, unique node number. Okay, and provides a means for communication between the nodes. It supports up to 64 masters. ACE is suitable for smaller and simpler systems. The way protocol is implemented, the way interconnect is implemented, it only supports smaller and simpler systems. Talking about Chai protocol, it supports, other than whatever ACE supports, it also supports atomic operations, memory ordering hints, the quality of service. So there are multiple things that Chai supports on top of ACE. It is suitable for larger and more complex systems. When we say more complex system having large number of masters, the slaves, that is the memories, peripherals, and memory controllers, all those things is what we mean by more complex systems. So this is a brief about difference between ACE and Chai protocol. Now let us now
sir,
talk about, yeah.
Sir, can you explain what is a cache line?
I will be talking about that. That is what I'm talking in this slides now.
Okay, sir.
Okay. So now let us talk about cache coherency. Okay. So as part of this, we'll be talking about what is a cache, that is cache line, what exactly is cache coherency means, what is a cache state diagram, and cache line, concept of Snoop, and concept of invalidate. So we'll be talking about all these things now. First, what is a cache? Cache is basically it's a memory which is sitting between CPU and the primary memory, system memory. Okay, the primary memory can also be called as system memory. Okay, which provides CPU with the quick access to the memory contents. So you can see, as you can see, this is more close to the CPU. So if it accesses something from here, access will be quick. If it accesses from here, access will be slower because it is connected through some interconnect or whatever, right? The latency is larger. Okay. So these things are called as caches. I'm sure all of you would be familiar with what is basic definition of cache. So let's read through that once. So what is a cache? It is a extremely fast memory, which is kind of implemented using SRAM cells. It's extremely fast memory that acts as a buffer between the DRAM and the CPU. So primary memory is the DDR memory. This is the CPU. This is a fast memory which provides CPU with the fast access to the frequently accessed locations. A cache memory holds frequently requested data and instructions so that they are immediately available to the CPU when needed. Okay. I hope you understood what is cache. Next, let's talk about what is cache coherency. I will also introduce the term cache line in the following slides. Cache coherency ensures that all processors are bus masters. It can be processor or a bus master within the system have same view of a shared memory. When we say same view, what we mean by same view is if one of the master is accessing address location 100, if let's say it's getting 25 data. As I said, other master, if it accesses 100, it should also get 25. It should not get a different data. So that is what we mean by a same view of the shared memory. Let's say one master has a private memory which no one else can access. Then it need not be coherent. Okay. Whereas when we say shared memory, it must be coherent. I mean, concept where if any processor accesses a specific location, they all should get the same data from that location. Okay. Cache coherency ensures that changes to data held in cache of one core. See, every core will have its own L1 cache, right? Whatever changes that you do into that cache are visible to other cores. Other cores also should see the changes to that cache line, making it impossible for cores to see stale or old copies of the data. It should not so happen that if I am accessing something, I get old data, this is getting latest data, then it is wrong. Then it is not coherent. Okay. So in this case, we are just explaining how does a coherent system look like. You see, we have got two processor subsystem. We have got one cluster, another cluster. Okay. In one cluster, there is two cores are there. Each core has its own associated L1 cache, and two cores have associated L2 cache. Okay. And my other cluster also has the same architecture. So the coherency concept applies to these cores also, clusters also, basically. Okay. So the coherency between them is maintained through cache coherent interconnect. There's a cache coherent interconnect which maintains the coherency for these clusters and core level. Next. What is meant by system level coherency? Let's understand. A system is coherent when all master are able to read the correct data from any valid address at any time. When to say what is the definition of coherent is, it is said coherent when all masters are able to read correct data from any valid address at any time. It removes the need for software cache maintenance. How it works? You see, there is a cache state diagram is there that ensures that when old copy of the cache line is written, other copies are invalidated. See, there is a state diagram which will tell the guidelines. What happens when I read a location, when I write to a location, so how it should be dealt. That is what these ACE and CHI protocols implement. Multiple copies of the cache lines can exist when other masters read the shared data. See, it is possible that multiple masters can have a same cache line data, but they all should be coherent. I hope you got a basic idea about what is system level coherence. Next, cache coherency types. There are two types of cache coherency. One is called as software managed coherency. One is the hardware managed coherency. Generally, whatever we have been talking more from a perspective of hardware managed coherency. When you go to software managed coherency, it becomes complex and it impacts the system performance, because it becomes the responsibility of the software to maintain the coherency. It essentially impacts the performance. So that is where most of the implementations prefer hardware managed coherency. In the hardware itself, you take care of coherency maintenance. First, in software managed coherency, software is responsible for maintaining coherency. When I say software, we are talking about device drivers. It clears the dirty data, old data from caches. In the software managed coherency, whatever dirty data is there, it is invalidated from the caches. It takes time, adds to software complexity. I mean, because software is taking care of the coherency, it adds the latency and can reduce the performance when there are high rates of sharing. See, when a lot of things are being shared, my software means the instructions that are executed by the processor are supposed to take care of the coherency. So that impacts the overall system performance. Next, talking about hardware managed coherency. Hardware maintains coherency between data caches within a cluster. A core automatically participates in the coherency scheme when it is powered up and has its Dcache and MMU enabled, and an address is marked as a coherent. See, in case of hardware managed coherency, there is no role of the software. The core itself automatically participates in the coherency scheme whenever you power it up and has its Dcache, means data cache and MMU enabled, an address is marked as coherent. So only for the address locations which are marked as coherent, coherency is maintained. For the locations which are need not be cache coherent, let's say some location is not part of the main memory, so you don't need to maintain any cache coherency for that. This hardware coherency, managed coherency, this adds to some hardware complexity. See, here software is getting complex. In hardware managed coherency, hardware is getting complex, and that complexity will increase the complexity of the interconnect, and to clusters also, because at the cluster level also they're supposed to maintain the coherency, right? But greatly it simplifies the software development, enables applications that would otherwise not be possible using only software coherency. So that is where you see it has got more advantages compared to software level coherency. For any cluster level coherency, they implement using hardware managed coherency. Next, let us talk about some of the coherency keywords. Like someone was asking, what is a cache line? So let's discuss all those keywords now. First, let's start with understanding the cache line. To understand the cache line, the best way is, let's take this diagram, whatever diagram I've shown you here. To this, let's understand. Let it be, let this slide be there. Okay. In this case, cache line is the basic unit of data transfer between cache and the system memory. Smallest portion of data that can be mapped into a cache is what we call as the cache line. Every mapped cache line is associated with the core line, which is corresponding region of the backend storage. When we say backend storage, we are mostly talking about the system memory. The cache line is generally fixed in size, typically ranging between 16 to 256 bytes. So first, let's understand what exactly is a cache line. See, cache line is whatever transfer that happens between the cache memory. There will be a cache controller here and the primary memory. Whatever communication happens between these two, it always happens in terms of cache line. So in this case, what happens is, whenever cache controller writes to the primary memory, reads from the primary memory, it always happens in a unit of cache line. Now the cache line can be 16 bytes, 32 bytes, 64 bytes, 128 bytes, or 256 bytes. Generally, the standard is 64 bytes. That means what? The whole memory is implemented as cache lines, as core lines. Each core line is the size of a cache line. Okay, so that is transferred into the cache memory. Okay, if this is 64 bytes, it will also be 64 bytes. So each memory is like 64 bytes. Please take a look at this diagram. So if you see, when we say system memory, I'm talking about this primary memory. Okay. Secondary memory refers to my hard disk, SSD, all those things becomes the secondary memory. This is the cache memory. Please take. So this cache storage is nothing but this cache memory. Okay, we can understand the whole DDR memory or system memory can be understood as core lines. Generally, core line is also a size of cache line. Now, cache line can be anywhere from 16 to 128 bytes in size. Sorry, 256 bytes in size. Now, mostly it will be 16 or 32 or 64, 2 to the power numbers, or 256. But for a system, it is fixed. For a given system, cache line size is fixed. We cannot change it. Once it is, let's say 64, it's fixed. Mostly the standard is 64 bytes. Standard is 64 bytes. The cache memory L1 and L2 caches are also implemented as basically implemented, understood as, I mean, they're like, everything is understood like a cache lines. The whole memory is distributed as cache line. You see, the whole memory is treated as cache line 1, cache line 2, cache line 3, so on. The primary memory is treated as core lines. Now, before we just get into the concept of cache, let's understand the role of a primary memory. See, when we boot up a system, let's say when we boot up a system or laptop for that matter, all the applications are loaded from secondary memory. That is nothing but SSD to the primary memory. Because it is quick to access. When we say primary memory, we are talking about DDR. It is also can be called as system memory. We can even call it as primary memory or the system memory. The systems want even better performance. The SoC wants even better performance. So that is where cache is introduced between processor and DDR. Okay, cache is introduced between the processor and the DDR. Now, more frequently accessed locations are stored into cache, so that when processor wants to access those locations, it can get it from cache instead of DDR. It improves the performance. Now, then you may say, fine, why can't everything be cache only? Why can't we just remove the primary memory? Why can't we keep everything as a cache memory only? Can someone tell me why are we not doing?
Because of the cost.
It's the cost. Basically, this is implemented using DRAM technology. This is implemented using SDRAM technology, SRAM technology, sir, not SDRAM, SRAM. Okay, it requires 6 transistors. This requires only 1 transistors. So automatically it is bigger in size and it is also more power consumes. I mean, it will consume more power because there are a lot more transistors involved. So effectively, primary memory will be relatively bigger, cache memory will be smaller. Okay, because of that, it cannot hold, the cache memory cannot hold the entire primary memory because it's limited in size. This is bigger in size. Okay, same thing applicable between primary memory and system memory. See, my DDR will be, let's say, 8 gigabyte. This will be 1 terabyte. Can it hold 1 terabyte? No. We only load the applications that are being currently accessed. For example, in my laptop, currently I'm accessing PowerPoint. I'm accessing XLS. I'm accessing Paint. I'm accessing GoToMeet, GVim. They are all loaded into my DDR right now. And those instructions are being accessed by the CPU. And it is executing. It is executing PowerPoint presentation. It is executing XLS, Paint, everything by accessing the application data from the DDR memory. But see what happens, even in that, I am accessing this presentation, CHI protocol, more frequently. Since 2 days, I have been accessing the same content. So my CPU understands that chai is the one which is being more frequently accessed to. So whenever I type chai, automatically it comes up with that information. So this is where the primary memory and cache memory holds the more frequently used applications, the more frequently accessed cache lines. Okay, so in the primary memory, it works at the application level, which applications are being currently accessed. Cache memory holds which locations are frequently accessed. Those locations, it will maintain the cache. Now, when we say location, it doesn't, there is a granularity for the cache. So the cache works at a cache stores the elements. Cache line granularity. So the access between cache and system memory happens at this granularity. I hope you understood. One student has asked a question. Let's address that first. Is the cache line is basically a data line, or if the cache line is 64 byte, then it means it can hold 64 bytes of data. See, cache line is a virtual notional division of the memory. Cache line is not a data line, not a data line. It is a notional division of the memory. For example, my memory is there, my cache is there. I will understand this part of memory as one cache line. This part of one memory is one cache line, like that. That is the cache line. So it's not the data line, that is what we are calling as a cache line. Prasanna, is it clear? Any other questions? Okay. So in summary, let's summarize what happens and where exactly cache and cache line comes into picture. My laptop is booted up. You are okay to go at this level, or if you are already comfortable with these concepts, then I can move on to the next aspects. Can someone tell, I mean, are you all familiar with cache coherency concepts? Because I don't want to teach what you already know.
No, sir. We want to know what is cache coherency and all these concepts.
Okay, fine. So let's say laptop is booted up. So what happens? The first thing that happened is all the applications and data is present in secondary memory. This SSD, HDD. Then what happens? There is a ROM, right? From where ROM has the immediate, I think, few things, the boot related code will be there. Here what happens? The processor, there is a primary processor. Every system will have a primary processor, primary core or processor. Starts booting from ROM, and then it moves to, it gets instructions from other memory, instructions from other memories also. As per these instructions, the application data gets moved, that is by means of DMA, from secondary memory to primary memory. Primary memory here refers to DDR. So whatever that is present in SSD, HDD gets moved to DDR. Generally, DDR will be, you know, right, will be anywhere from 4 gigabytes to 64 gigabytes in size, depending upon whether it's a personal laptop, whether it's a server. It could be even bigger, actually, I mean, much bigger also. Okay. So based on this, this will decide how many applications can you load. See, if I try to load 30 applications, my laptop will crash because the system memory in my laptop doesn't support the 30 locations loaded at same time. So to load some new application, I have to close some of these things. Only then my system will perform better. Okay, so the processor can only access DDR directly. Processor can't access system memory directly. Not system memory, secondary memory directly. It's always routed through the DDR. Okay, that is where DDR holds a lot of importance in the entire flow. Okay, so what happened now? As once you booted up the system, all the important applications, for example, in my case, the PPT, the spreadsheet, the GoToMeet application, the Vim, the Chrome, all these application data, instructions and the data. Because every application will have two things, the instructions and the data it is accessing, right? Is moved to DDR. Why we are moving to DDR? Because DDR provides low latency. See, accessing SSD and HDD will be time consuming. Generally, it will take more time. Accessing the content from DDR will be relatively quicker compared to SSD and HDD. That means what? Let's say if processor fetching something from L1 cache, let's say takes 2 nanoseconds, for example. Same thing, fetching from L2 may take 4 nanoseconds. Let's say from accessing DDR, let's say it may take 15 nanoseconds. SSD, it may take 30 nanoseconds. HDD may take 100 nanoseconds. I'm just giving a rough correlation. So that is where the advantage is, if some entry is present in L1 cache, latency will be very less because it's immediately next to the processor. Whereas L2 cache, it will be more, DDR will be little higher. So when you go to HDD, it will be even very high. That is where whatever applications you are accessing are loaded into DDR. Why we don't load into L1 and L2 caches? Because they are too small in size. L1 and L2 caches will be generally very small in size. Because of that, we don't load the applications into L1 and L2, we load into DDR. Okay. You may say, what is the need for loading? Because DDR is a volatile memory. See, DDR is volatile. Because it is volatile, when we power off, when the power is off, it won't hold applications. Can someone tell me what is SSD? Is it volatile or non-volatile?
Non-volatile.
SSD is non-volatile. Because of that, even when power is off, it holds the application. Same thing for HDD also. Hard disk drive. Okay. So that is where to reduce the latency of access, every applications which are currently being accessed are moved into the DDR from SSD to DDR or from HDD to DDR. That is done by a means of direct memory access. There will be a system level direct memory access. Through that application data will be moved. Even in those applications, there will be few things which I will be accessing very frequently. See, in that applications also, see, application is, what is application? Can someone tell me, when we say application, what exactly is an application for a VLS engineer? What is an
Data.
application? Application is nothing but a set of instructions. Now, it could be ARM instructions, it could be MIPI instructions, or any other processor specific RISC-V instructions. Right? Depending upon which processor we are working with, those set of instructions is what we call as the application, right? Let's say my PowerPoint is nothing but instructions, which is a huge set of instructions. So when we open an application, when we open PowerPoint presentation, let's say PPT application, what happens is those instructions, it will consider, let's say PPT instruction size is around 500 megabytes. The whole entry gets loaded. The whole instructions gets loaded into, gets moved to DDR. And the processor starts accessing these instructions from DDR. Now, even in that, there will be a specific address location where it would have been moved. Let's say 500 MB means they would have moved from 32 tick H 1000 to 32 tick H 123000 or 100 let's say. That means what? This PowerPoint, this much data is present between this location. Now I have taken a hypothetical case. See, 350 probably won't mean 500 megabytes. See, megabyte means 20. You need at least till here. 6 into 424. Yeah, that probably corresponds to 500 MB megabyte. Assume. Okay. So whenever I'm doing anything related to the PowerPoint, let's say I go here and do some change, that change will be, that corresponding instructions will be present in these address locations of the DDR. Now what happens is, there are in this address range, there are few locations which I access even more frequently, which I access more regularly. These locations are stored as part of cache so that latency can be much smaller. See, latency when you access from L1 and L2 cache, it is much smaller than DDR. So that is where those frequently accessed locations will be kept into cache. Now assume that those locations are, example, 32 tick H 100 0100, 32 tick H 100 0180. For example, these two locations. So when we say cache, we have cache line, we are not only talking about one location. If cache line size is 64 bytes, the one entry stored will be from 32 tick H 10100 to 32 tick H 10001 how much? 3F. Can you tell me how I came up with number 3F? Because if you convert 64, it comes to tick H40. So if it starts from 0, it has to go till 3F. So one cache line will correspond to this entire data in this range. Okay. Similarly, the other cache line will be stored from 802. What is the next one? Can you tell me? BF. So here the assumption is what? These are the two frequently accessed locations as part of the PowerPoint presentation application. See, my processor is frequently accessing these two locations. So it won't be just 100. It refers to the entire cache line range. So this is the basic unit of transfer between the cache and the DDR memory. So when we say processor is fetching, let's say, for example, here processor decided that 32-bit H1000, this one should be part of cache. But let's say, that entry is not present in cache. What it will do? The cache controller will. So my processor will give an instruction saying that processor will give a type of instruction where my interconnect cache controller understands that this entry should be created in allocated in cache. So because it understood that this entry should be created in the cache controller will read to the DDR memory, fetch the data at 32-bit this location. So the point is, it doesn't just get one location. It gets entire data. That means what? The 64 bytes of data. That is the basic concept of cache line. So anytime you are accessing any location in between this range, you have to get the entire cache line data. So that means cache line is the basic unit of data transfer between cache memory and primary memory. But that is not true for this one. If you take this one, it is not true. Sorry, where is it? Here, between these two, it is not true. Here only the concept of cache line is present. This can access in a different sizes. But when it comes to the cache memory and the primary memory, DDR memory, the basic unit of communication is the cache line. I hope everyone understood. Now, then you may say, what is the challenge in this? It's very simple, right? Then why do you need complex protocols like CHAI protocol and all that? See what happens. The overall cache hierarchy is more complicated than what you see here. Every core has its own associated L1 cache. A cluster of cores has a L2 cache associated with them. Then you can have multiple such clusters, as you would see in the next slide. Okay, so you can see this core has L1 cache, this core has L1 cache, this has L2 cache, this has L2 cache, and these cluster level maintenance, coherency maintenance we have to do. That is system level coherency maintenance we have to do. So because of that, the concept of coherency gets complex. Now you may say, what exactly is the coherency here? Is if this core is performing some write into this location 100, my coherency interconnect should make sure that gets reflected into other caches also. If they are holding location 100, they should also be updated. If you don't update them, then it becomes non-coherent system, because it has got a different view of the location. So that is where it is not coherent. I hope you got the basic idea. Now coming back to this, let's quickly revise. So what is an application? When you open application, what happens? We have discussed that. Then we discussed that for a frequently accessed locations, if the cache line size is 64 bytes, what happens? I have told you this part. And now here what happens is, there are, because cache line size is limited, it can hold only, hold limited number of cache. Whereas DDR has much bigger size, right? DDR will be much bigger in size. So it will hold a larger amount of core lines. So there we need to maintain the cache lines. We need to maintain cache lines. That means what? Sometimes you remove some cache lines, add new cache lines, evict some cache lines, remove or add a new cache line, and maintain coherency with other caches, maintain coherency with other caches. So all of that need to be done. This is where we need a protocol which will take care of all these things. That is where the Chai protocol comes into picture. Even the same thing is what ACE protocol also does. But as I said, ACE is for a smaller systems where there are small number of masters, a less number of masters, whereas Chai is meant for much complex systems. So any questions so far?
This conference is no longer being recorded.
Let us just take a break for 10 minutes and we'll meet in 10 minutes. Hello everyone, let us resume the session.
This conference will now be recorded.
Okay, so before the break, we were discussing about what is a cache and what is a cache line, and we did discuss about what is how the communication happens between the processor, cache, and the system memory and the secondary memory. Okay, there are some locations which a processor can directly access into the DDR. It doesn't want it to be part of the cache. Okay, for those locations, there is no need to maintain the coherency because they are directly being accessed from the primary memory. Okay, but this path doesn't exist. I mean, processor doesn't directly access the secondary memory anytime. Next, any other questions before we move on to the next topic, next part of the coherency? Okay. So now talking further about cache, there are two types of caches. One is write back cache, one is write through cache. First, let's understand write back cache. So write back cache simply writes to the processor's local cache. Like local cache is like L1 cache or L2 cache, and then lets the processor continue its normal operation. See, we won't update. Let's say we are writing to location 100. Location 100 is updated here. It will not be updated here. Okay. It is the interconnect which is responsible for making sure that it is updated here, here, and here. Okay. During the whenever we need to evict that location, that means we need to remove that location from the cache and add a new location, then only the data will be updated into the system shared memory. That type of caches are called as write back cache. See, if you read it now, the write back cache simply writes to the processor's local cache, then lets the processor continue its normal operation. Data in the cache is written to its final destination later. So data in the cache could differ from data in the storage for short period of time. I told you, right? See, I may have some data in cache which is different from the shared memory. Okay. Then you may say, how can other core get the right data? So other core, whenever it makes a request, it goes to the cache coherent interconnect. It will first check with the other caches. Do you have this updated data? Based on that, if it has the updated data, it will give it. So my access will not happen to system memory, shared memory. Okay. So that is how even the other processor will get the proper data only. Further to it, the principal purpose of write back cache is to effectively boost the computer performance. Because when you do write back means what? What is the meaning of write back means? At later point of time, we'll write into the shared memory. Right now, all accesses will only happen here. Sometime later, we'll update into the shared memory. Because of that, performance will increase. So the other type of cache is write through cache. What is write through cache is? Write through cache halts application processing until data in the cache is also updated in the main memory or disk. I mean, whatever update you do to the cache, that should get updated to the main memory also. That is the system memory or the DDR. This ensures that cache and storage data are always consistent before an application is allowed to continue. Most of the times we are talking about the coherency for write back cache, not for the write through cache. Okay. Now, what exactly is a cache coherent interconnect? If you refer to this diagram, this is the interconnect which takes care of the cache coherency. It has got some additional signaling through which it maintains the coherency. It ensures that if something is updated here, it is reflected here, here, and here also. Now, you may ask, is this how the AMBA-CHAI protocol coherency works? The fundamental concepts remain same, but it won't have anything like cache coherence interconnect. There will be a different way in which coherency is maintained. So we'll talk about all those things as we go forward. So here I'm just giving you an introduction to the concept of cache coherency. In the write through cache, the performance will be impacted because every time you update a cache, that should also be updated to the main memory. Now, what is cache coherent interconnect? Coherent interconnect that enables the hardware coherency. In hardware coherent systems, an operating system can run over multiple processor clusters without complicated cache maintenance software. Means basically, when you say hardware coherency, it is the hardware which is responsible for taking care of the coherency. So you don't need a software to take care of that. So hardware-based I/O coherency is used by transaction hosts using ACE interface protocol or similar protocol. Like when we say similar protocol, we are talking about CHI protocol in the ARM-based processor subsystems. So the hardware-based coherency is implemented either through ACE protocol or CHI protocol. The cache coherency interconnect can issue Snoop request to the ACE interfaces. Similar concept Snoop request will be there in the CHI protocol also, which will take care of which are used to take care of the coherency. And they use its Snoop filter table to determine if a memory location is cached. If there is a cache hit, the data is returned to the source. When the transaction is not non-cacheable or the memory address of the transaction is not there in the cache, that is a miss. The cache coherence interconnect operates like a regular interconnect and forwards the transactions to the memory address location, memory address destination. That means what? Let's say it wants to read a location 100. What my cache coherence interconnect does is, you see, ACE compliant interconnect, that is cache coherence interconnect. It will check with the other masters. Do you have that cache line? It will check, do you have that cache line? If they say, no, I don't have it. Other masters also say, I don't have it. Then it knows that no one has the cache line. So it will go and fetch the data from the main memory. Whereas if other caches have the entry, let's say it has got the entry. When it sends a request, it will say that, yes, I have the entry, and it will provide the data. So the data, whatever comes here, it will be given here. So you don't have to now get from here. So this is how ACE protocol implements the coherency. The process of interconnect asking, do you have this entry? That is called as snooping. What is meant by snooping? The process of checking what is your status, what is happening with this cache line. That is called as snooping. Okay. I think I have already shown you this diagram. Now let's understand the concept of cache line states maintained in the cache. So I think this diagram is a bit confusing. I'll explain through different diagram. Okay. Imagine a system. Are you all comfortable till this point? Any questions you have?
No.
Okay. So what is meant by cache line state? If you look at ARM based systems, every cache line in ACE protocol, let's take ACE for that matter. In case of ACE, every cache line can be in one of the 5 states, either invalid, clean, or dirty. Clean means can be unique clean, shared clean. Dirty again, unique dirty, shared dirty. So you see, if you take the overall combination, there are five combinations are there. The cache line can be invalid, or the cache line can be, it's like this. Cache line can be invalid, or it can be clean. It can be valid, either invalid or valid. If it is valid, it can be clean, it can be dirty. If it is clean, it can be unique or shared. If it is dirty, it can be unique or shared. So totally, you see, there are 5 combinations are there: invalid, unique clean, unique shared clean, unique dirty, shared dirty. So totally 5 states are there for any cache line. It means to say, if I have a cache memory, Let's take like this. If there is a processor 1 as a L1 cache of, let's say, how much size? 8 kilobytes cache. Let's take hypothetical, okay? If cache line is processor 1 or core 1 has L1 cache of size 8 kilobytes. Each cache line is 64 bytes in size. Can you tell me how many cache lines are there totally? There in core 1 L1. Core 1 means processor 1 L1. Can someone tell me? Totally 128 cache lines will be there. How did I get 8 kilobytes divided by 64 is 128? Because my total memory size is 8 kilobytes, whereas my each cache line is 64 bytes. So if I divide 8 kilobytes with 64, I get 128. Just for convenience, let's take a smaller number, 4. So it will be 4 kilobytes divided, it will come to 64. So totally 64 cache lines are there. So that 64 cache lines, I can imagine like this. It is this is what constitutes the cache lines. So each cache line has a state. Let's say this is cache line 0. Constitutes the 64 bytes. It has got a address. It has got one address. Let's say address could be 32DH1000100. You remember, right? One of the cache lines I said, cache line 1. I don't need to write 64 bytes. Understand that it's 64 bytes. So this will be the starting location. End location will be plus, see this plus. I mean, I'm not able to do hexadecimal calculation, but it will be like 013. Let's say cache line 1 is some other location, 32DH. Let's take 1, 2, here only, here also it will become 1, 2. Now it can be any random locations for that matter, like this 1, 2. Totally 64 cache lines are there. For each cache line, there is an address and the corresponding data. The data also will be there. So 64 bytes of data will be there for every line. It's like an associative array where you have the address location and the corresponding data. So this is the address of the cache data that is present in the memory, and this is the data. So like that, for every cache line, there will be this data. Each cache line has a state. Each cache line has a state. In fact, then I don't need this. Here itself I can write CL0, CL1. And CL16. Okay. And there is a state. State means each cache line can be the location, the end location. End location is for our purpose. Okay. The data present in cache line. I think the state is a very important concept here. Now this state can be either invalid, it can be unique clean, it can be shared dirty, it can be unique dirty. It can be shared clean. Like that, each entry has one of the five possible states. Of the five possible states. So whenever processor issues some transaction to one of these address locations, accordingly, this states gets updated. So my processor one cache controller holds this entire information. Mean what is the cache line, what is the state, when an access happens, what should we do? That it takes care. So this state of a cache can be one of the five only in case of ACE protocol. If you go to Chai protocol, it can have 7 possible states. Instead of 5, it will become 7 states. This plus 2 more states will be there, which we will talk as we go forward. Have you all got a basic idea about how a cache looks like? What exactly we mean by a cache line and what is mean by a state of a cache? Okay, now let us understand little more about what is meant by invalid, what is meant by unique clean, what is meant by shared dirty, so that you can understand this better. So, what is meant by invalid is that entry doesn't exist. That entry, that location, the location is not present in the cache. That means if we say that this is invalid, this location is not valid anymore. If processor wants to access this location it cannot access from the cache. It has to get from the either other cache or from the system memory. That is what invalid means. Unique, when we say unique clean,
Sir,
yeah,
invalid in the sense if there is a cache miss also, then it is going to be invalid only.
cache miss, when it is invalid, it will be cache miss. Yes.
Yeah. So we can say like that if it is a cache miss, then it is invalid. Like that, or what is
Not
the
like that.
difference? Then
See, the cache maintains a state for each cache line. See, I can invalidate a cache location. See, what I can do is processor can generate a transaction. Processor can do a transaction where it wants to evict an entry, a cache line, the cache. When it is evicted, let's say till this point it was unique clean. Once it is evicted, it will become invalid. Got it? Now, if processor wants to read from this cache location, it results in cache miss. Understood?
Yes, sir. Thank you.
Now let's talk about what is meant by unique clean. Unique clean means, you see, in a system there are multiple masters are there. Each of them can maintain a cache lines, right? Different cache lines. It is possible that the same cache line is present in other caches also. It is also possible that it is this address location. This is only part of this processor cache only. That means what? If it is unique clean means no one else is holding this cache line. No one else is holding this cache line. The address location 12000100 is only part of the processor L1 cache. No other processor cache has this entry, and that is unique. Then you may say, what is meant by clean? It is clean means it is up to date. Whatever data, since it is unique clean means this 64 bytes of data is up to date with the system DDR memory content. Means both of them are same. Whatever data I have here in my cache line, that's it, the line 11 means cache line 11. Whatever data I have here and whatever data that is present in DDR, both of them are exactly same. Whatever changes that I have done, those changes are reflected into the system memory. So in those cases, it is called as clean. What is meant by dirty? I have done some updates, but they are not updated here. Let's say I've updated it to 27, but here the data is only 14. So this is different from this one, right? In that case, this entry is called as dirty. Entire cache won't be dirty. Entire cache won't be dirty. One cache line will be dirty. One cache line will be dirty. If you say this is unique dirty, means unique dirty indicates that this 64 bytes location or this 64 bytes only this unique dirty means this address is only cached in this core 1 in core 1 L1 only. No other processor has this address entry in their caches. And what is meant by dirty means dirty indicates that this location, this core 1 L1 entry data is not up to date with the DDR memory content. Means DDR memory has a different data and my cache has a different data. That is what we mean by dirty. So unique means one thing, like I hope you got it. U means unique means only I have that entry location. Dirty means whatever entry I have, let's say this location I call it as 563467006720. Okay, for example, this would be what 563467 5F. I just have to add 3F because size is 64 bytes, right? The size is 64 bytes, so the difference will be 3F. So this entry unique dirty, it indicates that this location is only present in L1, the processor 1 L1 cache. No other cache has this location. Okay. What is meant by dirty here is this entry data that is present in my core 1 L1 cache doesn't match with the DDR memory entry data at this address location. That is called as dirty. Now let us talk about shared dirty. Let's say this is 32-bit H 469213448, something like this. Okay, because it is shared, multiple different processor caches have this entry, this address location cached. That's what we mean by shared. Then what is meant by dirty? You know, dirty meaning you know, right? Dirty essentially means that it is responsible for the one of these cores, one of these processors who has this entry as dirty, who has the dirty entry, dirty mark. They are responsible for. They are eventually responsible for updating DDR memory with the correct data, with up-to-date data, the correct data, with the final updated data, final data. You understood the whole point? Means dirty indicates that my entry is not up to date with the, let's say if I'm in dirty, my data is not matching with this data. Eventually, it is my responsibility to update this with whatever data I have so that this and this will match. Then I will move to clean state. Next, shared clean means same thing. You take the same thing. If I say shared, clean means what? This core L1 entry data matches with DDR memory content data. Is what we mean by shared clean. Shared clean. Now this could be some random location. Let's say 32 TH, 4394, something like this. Like I have 64 cache entries in this processor one for L1, core 1 L1. I can have one more core. Like you see, if I minimize it, there could be one more such core, okay, which holds other set of caches. I mean, see, I can take like this. This is core 1 L1. To go back to this diagram, I can have one more entry here. I can have core 2. Core 2 means what? This is the core 2. This is the processor 1. This is the processor 2. It will have its own caches. It will have its own cache lines, which are not same. Now it could be something else. This could be something else. This could be something else. Let's say 32 TH. This could be again 32, something else. Something else, what I did is see, both these are matching. See, this one and this one are matching, right? So this is where the coherency comes into picture, because this is also holding the same address location, this is also holding the same address location. They should have the same view of the data. Whatever data I have here, thus it should also have the same view of the data. That is what we mean by cache coherency. Okay. Like this, different entries will have different data. Okay. Similarly, core 3, depending upon how many processors are there in a cluster, they all will have different entries. Okay. It is the responsibility of this interconnect to take to handle that. So we'll discuss this further as we go forward. But I hope you got a basic idea of what is meant by cache state. It is when we say cache state, it is not the entire cache state. It's one line. This is one line, cache line 0 at this location. What is the state of that? Is it valid or invalid? Invalid means what? This location is invalid. It's as good as not present at all. It's as good as not present. When we say unique clean means what? Only this cache line has the data. No other cache line has this address location cached. Like that, we have understood other states also. Understanding Chai protocol is all about. I mean, what is involved in understanding Chai protocol is because to maintain cache coherency, okay, and whenever processor 1 does any transaction, it is the responsibility of Chai interconnect to update other caches for this transaction, so that they can also update their cache state. One more thing is, when we say this entry is in unique clean, it will never be, it's not like it will always be in unique clean. It can change. It can go from unique clean to shared clean. It can go from unique clean to unique dirty. So all those changes will happen. That is what we mean by the state diagram. So one of the state diagram looks like this. Okay. It is in shared state. From shared state, it can go to invalid state. From shared state, it can go to modified state. So all those things. Now you may say, what is shared, what is owned, what is modified? This is the definition. Unique dirty means modified. This is UD. Shared dirty means owned. I can even take this. So modified is what? Unique dirty, UD. U. Shared means what? Owned. Share. Owned. Sorry, owned is shared dirty. Sorry, shared dirty. Shared means what? Shared clean. SC. Exclusive means what? Unique clean. This is invalid. I anyway. So, understanding Chai protocol is about understanding this state diagram. Chai state diagram will be little more complex because you see this has got only 5 states. This has got only 5 states. The Chai protocol will have +2. 7 states will be there. Because of that, this will be little more complex. The state transition will be little more complex than what you see here. Now, what this diagram tells you is, this diagram tells one of the states of a cache line. We are talking about one cache line state diagram. I mean, this cache line you see here in our XLS, there is one cache line, this one. So we are talking about cache line 1. Every cache line follows this state diagram. Every state cache line follows either MoA-C or MoC state diagram. There are different types of state diagrams. So these state diagrams indicate how a cache line change its state when a transaction happens. Now the transaction can be write, can be read, can be evict, can be clear, clean, can be snoop. So that different types of transactions. When a specific transaction happens, how the cache line state should change. That is what is indicated by these state diagrams. So that is something you can see here. What does this tell is, for example, one of the locations, okay, is in invalid. Let's say, what is that location? Let's say cache line 0 is in invalid state, right? Cache line 0 is in invalid state. Now, someone did a read miss shared. Read miss shared means what? They have performed a read. They are accessing a shared location. They want the location to be shared. Whatever location they want to read. Let's say I want to read one location. Once the read happens, I'm okay with that entry present in other memories also. See, what is that means? My processor has performed a read, okay, to one address location. That entry doesn't present in my cache because it is a read miss. Okay, and I'm okay with that being present in the other cache lines also. Then I will go to shared clean. That means what? Since I'm sharing the same entry with other caches also, I'll be in share. And since I'm reading, whatever up to date data will be there, I will get that. So because of that, it will be clean. So that will be shared clean. So what it tells is, whenever you are in invalid and there is a read miss happens and you are receiving a shared kind of access, then the next state will be shared clean. For example, you have done a write. Your entry is in shared clean. Let's say one of the entry, you are in shared clean state. Now, someone did a write. I mean, the processor has done a write to that location. What happens? Your data is modified, but it is not matching with the main memory data. See, I have done a write. This entry, but that entry, whatever I write, it won't match with this one, right? Because I have only updated my local cache line. So since it won't match with this will be called as dirty. Since I'm updating this one, and this will get invalidated. Whatever entries that are present in other things will get invalidated. So it will go to unique state. So it will be unique dirty state. So this is what this state diagram talks about. So in summary, what happens is each of the overall cache is divided into multiple cache lines. Each cache line can have one of the 7 possible states. In case of Chai, 5 states in case of ACE protocol. In case of ACE protocol, 5 possible states are there. In case of Chai, it will be 7 possible states. So when master 1 or other master does some transaction, it can be a write transaction, it can be a read transaction, any type of transaction, okay, or clean transaction or a evict transaction. Okay, there is a cache coherence. Cache coherency interconnect will be there. Coherent interconnect will be there, which takes care of the cache line changes, state changes. Now, once the change happens, this shared clean or unique shared clean, right? Shared clean will move to unique dirty. Address will still be same. Address will be still be same. Why it will move to unique dirty? Because the master, the core one has performed a write hit. It has done a write to the existing location in the cache. So my master has done a write hit. I was in shared clean. So my state will change from shared clean to unique dirty. Because my data got modified, right? My data got modified with respect to the main memory. Whatever data I have here, whatever data that is present here, they don't match. Because of that, I will become dirty. And because I'm updating, other locations will get invalidated. Because I want coherency, right? What do I mean by coherency? My entries should be matching with other entries. If not, I want to evict them. I want to remove them. So if I remove them, I'm only left with the data unique, and I'm dirty. So my state will be unique dirty state. Did you all understood? So,
Sir?
please ask.
Yeah, could you explain me this about unique data once again? I want to say how it is going to be modified like that.
No, what I see what happens. If a system consists of many processors, or it's a cores, each core has its own associated L1 cache and group of cores has L2 cache. L2 cache. Multiple clusters have. Anyway, let me not introduce the concept of L3 cache. Right now, this is fine. What happens is each of these caches, each of the above caches, has cache lines. Let's say 64 bytes in size. That's each. When each of these cache lines, see, when we just restart the system, I mean power up the system, the entire cache lines, there are no entries in the cache line, right? There are no entries in the cache line. So all lines are invalid initially, because when I power up, there is nothing in the cache. So there is nothing in the cache. Because of that, all the lines will be invalid. Now, when processor 1 issues a cacheable read to a location, let's say location 100, then what happens? What will be the state? Let's understand what will be the next state. Let's understand. That is what this state diagram tells. See, you are in which state? Tell me initially. Address location 100 is in which state right now? Initially.
Invalid.
Sorry, it is in invalid state. Now, where do you think it will go to? Where do you think, which state will it go to? Can you tell me? Did I do probe write hit? No. I will explain what is probe write hit. Basically, this is what has happened. I have performed a read and it's missed. My cache doesn't have it. Initially, it's invalid. So I'm reading location 100. I'm reading location 100, but that entry doesn't exist. I'm reading my processor 1. The processor, just call it as core 1. Core 1 is reading at 100. That location doesn't exist in the cache. So it will result in, read will result in miss, right? Read will result in miss, cache miss. That means what? Read miss. Because of that, see, when you are in invalid state and a read miss happens, this arrow indicates that you will go to shared state. So now entry at 100 gets created in cache. Which cache? Core 1 L1 cache. And the state of that will be shared clean. It will be in the shared clean state. Now, after some time, core 1 has done a write to address location 100 with some different data. You see, this write I did, this write has only happened to core 1 L1 cache. So it is not, it won't match with, it will not, surely it won't match with DDR data. Because DDR is not up to date, right? So this location will be dirty. This location is dirty. And the other thing is, since I am updating my memory, what my interconnect will do is, because this is updated, it will invalidate these two. Other memories it will invalidate. So I will be in only unique state. My location will be unique. The core L1, core 1, L1 will only have this entry. So what is the summary? Unique, dirty. So what is unique, dirty? Modified state. So my next state will be, if I am in shared clean and my master performed a write hit, I will go to unique dirty state. If now you may say, is this the only possible transition? No, there is one more transition possible. Some other master performed a write to their location. Let's say I have an address 100. Some other master performed write to 100 here. So this got updated, right? So because of that, it will become dirty. Since it is getting updated, my location will be evicted. So I will go back to invalid state. That is called as, if some other master accesses it, that is called as probe write hit. When we say probe write hit, means some other master writing to the same location. In that case, whatever entry I have should get invalidated, right? Because my entry is not up to date now. Because at some other point, some other master has performed a write to the same location. So my location will get invalidated. So I will move from shared clean to the invalid state. Someone had a doubt. Is it clear now?
Yes, sir.
So this state diagram explains how these state transition happens for the cache lines. Understand, this is not entire cache state diagram. This is the state diagram of each and every cache line. So if I have 64 entries, you see here how many entries I have? 64 entries I have. So each entry will have its own unique state, either invalid, unique clean, shared dirty, based on the transactions that happen, that are done by the other masters or the same master, the state transitions will happen. So in this case, let us understand one keyword called as what is meant by probe write hit, what is meant by probe read hit, and what is meant by read miss, what is meant by write hit. So all those keywords, if we understand, understanding the state diagram will be very easy. So what is meant by probe write hit? Let's some other master is doing a write to a cache location, to a location, to location 100, let's say. I'm just taking 100 for convenience. So the interconnect, the cache coherent interconnect, CCI, will do probe write hit to other masters. Some other master means, let's say M2 in this case, to other masters like M1 and M3. It will check. So CCI, cache coherent interconnect, is telling, you see, M2 is writing to its local cache. So I am indicating the same thing to you. I am indicating same thing to you. You take appropriate action. Take appropriate action. Right. What is meant by appropriate action is, since master 2 has done an update, master 2 has done update to its cache. So I got the same notification. So I am telling you that that update has happened. So this, it will tell that probe write hit, probe write hit. So this master will decide what to do. In this case, it will decide that it should go to invalid state, because if the probe write hit happened, I'll move to invalid state. So this is how we understand the state diagram. We'll talk more about the state diagram and how the state transition happens, all that through detailed example. In the next session, we'll take some examples and see what will be the initial state, when some read happens, when write happens, how the state changes happens. All those things we'll discuss in the next session. So this is a brief about cache and cache coherency. In the next session, we will continue with the other aspects of the CHAI protocol, and also we'll talk a little more deep into cache coherency. So we will stop the session here. Any questions before we end?
Sir, can you show us the, say, other two states, right, in CHI? Can you show what are the other two states?
Other two states are?
Yeah.
I will show you. Unique dirty partial, unique clean empty. This is the other state. See, either cache line can be valid or invalid. In the valid, it can be unique, it can be shared. In the unique, it can be dirty or clean. Even in that, it can be unique dirty, shared dirty, and it can be unique dirty partial, unique clean empty. So there are these are the 7 possible states of the cache lines.
Okay, partial data in the sense partial data is going to be valid like strobes. That's it. And
yes, it is similar to that. It has got different meaning also, not just partial data. Part of the cache line, yes.
Okay. Yeah. Empty means all the, all the data is going to be.
No entry is there, but I'm still the owner of that cache line. I still have the ownership, but no data is valid.
Okay. Yeah.
So we'll be understanding more of this cache line states and everything, because understanding these concepts is very important to learn the chai protocol, because chai protocol is all about these state transitions, understanding when a transaction happens, how this state transition happens, and all those things. That will plan for next session. Any other questions before we end the session?
No, thank you.
Okay. So let's stop. Okay.
This conference is
We
no
will
longer
be
being recorded.
continuing the session from next Saturday onwards, because as I said, it's a weekend course. So next session will be on coming Saturday around 10 a.m. Those who are interested in enrolling, you can enroll uh, into this link. There is a link. E-transfer. Okay. Uh, if you have any doubts, any clarifications, we can discuss them in the next session in more detail. Like if let's say you and one more thing, we'll also provide you with the recorded video of these sessions, at least for 1 month, so that you will be able to revise the topics. Once you have gone through the video, if you have any doubts, we can even discuss them in the next session. Some other topics like, do you need to know ACE protocol? Do you need to know cache coherency? Not required. Everything will be taught from the basics. Even if you don't know what is ACE protocol, we will cover all the concepts from scratch. Any other questions before we end the session?
So, will you provide any materials like PPTs and PDF like that? Any materials?
PPT will be there. Whatever PPT I'm using, I'll upload it to the e-learning portal. From there, you can access.
Okay.
Okay, that's all right. Thank you, everyone.
Thank you, sir.
Just